Hello. Today I would like to talk about an important distinction in algebra. A distinction that, simple as it seems on the front end, is actually the source of many, if not most, of beginning algebra students' mistakes in algebra. If once understood and deeply internalized, this distinction is kept clear in the student's mind. Many of the common typographical errors that hold students back from understanding how algebra works can be quickly dismissed. Let's begin. The distinction I want to discuss is the distinction between terms and factors. Stated simply, terms are things that are held together by addition. An example of separate terms might be something like 3x squared is one term, whereas 4x is a second term and 1 is a third term. We can say that these are the first term, the second term, and the third term. A factor, on the other hand, can be thought of, at least at the beginning, as looking at one of these closer. If we consider 3x squared, we might observe that it is made of a 3 times an x times an x, and we would refer to the 3 as the first factor. X is the second factor, and the third factor is the second x. So one way of looking at terms and factors is to say we have the separate terms, and then within each of the terms there's the capacity to have multiple factors. That's not always the case. Take the 1, for example. That is a single term 1, and it is made up of one factor 1. Now, where it gets more complicated is we can actually see these terms and factors nested inside one another, where you can have a factor that contains terms, and those terms can contain factors. And as this structure builds in complexity, students often get themselves boggled down on what things belong to what, and what is a term and what isn't a factor. And many of the rules of algebra hinge on these are rules you're allowed to apply to terms, and these are rules you're allowed to apply to factors. And when students confuse and cross those rules, they get themselves into trouble. So to begin with, I want to pull in another topic, an idea called chunking. This is an idea that comes from computer science and psychology, but we see it well expressed in mathematics here. The idea is simply, when we look at something, do we think of it as being made of many, many individual little pieces, or do we think of it as more of a holistic component? At a physics level, we might say the components of the physical universe are protons, electrons, and neutrons. But we don't observe those with our eyes, nor do we even observe molecules with our eyes. We look at things as chunks in the sense of I am me and you are you, and this apple is an apple, even though this apple is actually made up of many, 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 many molecules and many, many, many atoms. But we don't see it that way, and we don't think of it that way, or we'd quickly be overwhelmed. There's too many things to keep track of. So we have this habit of seeing things as a whole, even if they are made of many parts. A great example, going back to elementary school, is when we begin to read. A beginning reader may see the word cat as 3 objects: C, A, and T. And then within each of those objects, they have a certain amount of vocabulary that they need to memorize. They need to remember that C goes with a K sound. They need to remember that A goes with a sound. And they need to remember that T goes with a T sound. They may even have to think about the idea that there is a long A and a short A, and we have to draw the distinction between, should we pronounce this cat or should we pronounce this Kate? And those are very big different things. So the idea in the psychology level is, as long as you're thinking of 3 separate objects, this is a fairly sophisticated idea. But as soon as we can move past that, we familiarize ourselves with the vocabulary, and we get comfortable to the point that we are thinking this way, then cat becomes a single object. And the comparative that I want to make here is cat is a little like factors, C, A, and T. But the whole word cat is a little more like a term, where we chunk it together and it becomes a single object. And then we move beyond that. Simple sentences can themselves become single objects, or whole paragraphs can become single objects, or chapters in a book can become single objects, so that you are able to pull more and more information together as a single idea and function with it. Another simple example is phone numbers. Now, these days, most of us don't memorize our phone numbers anymore, but there was a time in the past when you would memorize a prefix and you'd memorize a number and you'd memorize a second number. And in this phone number, if you think of it just as a 10-digit number, it's a lot to memorize. Now, granted, I'm using 5555555 here because I don't want anyone to get random phone calls. But memorizing a 10-digit number is memorizing 10 things, and it's a big job, but most of us don't memorize things that way. We memorize the area code, we memorize the prefix, and we memorize the 4-digit code. And so this becomes, in our minds, merely 3 chunks. And if we fast forward a few years before cell phones, oftentimes these were just a given. All of the people you associated with lived in the same town as you, and so had, or the same state as you, and so had the same area code. And then if you don't live in an overly large city, often the 3-digit prefix, there was only 2 or 3 of those to a medium-sized town. So really what you were memorizing was a single 4-digit number to remember your friend's phone number. So it became fairly easy to do. And that's what chunking gets you. Chunking is what helps a skilled chess player think 3 moves ahead. Chunking is what helps a computer programmer think in terms of larger objects like arrays or tables or strings instead of individual symbols. So too in algebra. Chunking and the ability to draw a firm distinction between what is a factor and what is a term will get us to most of the important things that we need in algebra. So let's pull in some vocabulary that we need to practice here. The kinds of objects that this type of student will be looking at as they're working through here are things like this. This is our first type of object. That's referred to as a polynomial. Now, there are many subcategories of polynomials. There is what we refer to as a monomial. A monomial is just a single term. Some examples of monomials would be 3x squared. They don't need to be that simple though. They can get more complicated. You could run into a monomial that looks like -3/4 x to the 5th, and that is still a monomial. You could even run into one that looks like 3x to the 5th over 4y, and that would still be called a monomial. We would, in that case, typically rewrite it as 3/4 x to the 5th over y, and this helps us make a distinction of a few other pieces that we like to look at in a monomial. The term at the front is referred to as a coefficient, and this is referred to as the variable structure. So when we see something like this, here too is a coefficient, and here too is the variables. When we see something like this one, we see that it's a little bit confused, and this is where the first amount of chunking kind of comes in. We could look at the numerator at the top and say, well, that has a coefficient of 3 and the variable structure is x to the fifth. We could look at the factor in the bottom, and we could call that a coefficient of 4 and a variable of y. And we might be tempted to start saying, well, there's two terms there. There's the numerator term and the denominator term. And you may even see that printed in books, but that's not a proper distinction. These should be referred to as adjoining factors. 3 times x to the fifth divided by 4 and divided by y are all 4 separate factors. If we write it in the standard forms, we would say that 3/4 is the coefficient, and we'd say this whole thing is the variable structure. But we can also break it apart to all of its components. And fundamentally, when we see something that is made up of factors, they are held to each other by multiplication and division. And it doesn't matter which, because we can always remember that the operation of dividing means the same thing as multiplying by the reciprocal. So all division is really multiplication. In a similar way, when we see terms, they can be separated by additions or subtractions because all subtractions are really just adding negative numbers. So there really is only multiplication and addition. Factors have to do with multiplication, terms have to do with addition. So if that's a monomial, then the next obvious thing would be to say there could, of course, be a binomial. Some examples of binomials might be something like 2x plus 1 or 3x to the fourth minus 7y. Those are both binomials. Notice they can contain different exponent structures, different coefficients, and even different variables. But the key thing is they're made up of 2 terms, and that's where we're getting bi. Binomial is a 2-term object. A monomial is a 1-term object. And then third, we have trinomials. Of course, this could go on forever. You could have quadrinomials, septinomials, dodecanomials, whatever you'd like, but we limit ourselves primarily to talking about monomials, binomials, and trinomials because the main operations that a beginning algebra student needs to work with is monomials, binomials, and trinomials. So we stop there. So a trinomial might look something like my first example. 3x squared plus 4x plus 1 would be a trinomial. Again, it could also be more complicated than that. It could be 3x to the fourth plus 4x cubed plus x squared, or any other variation of coefficients and integer exponents. I will go back to say that about polynomials. A polynomial will be made up of things where the exponents are integers. And in that sense, something like this example is a little bit of a stretch. We have here a y to the first power written in the denominator. That is an atypical thing to see for a polynomial, and technically we should probably call that a rational function instead because it's made up of a ratio. But the main idea I want to carry across here is that understanding what is the coefficient and what is the variable is very important, and this was used to illustrate the idea that sometimes that line can feel a little bit blurry, but we need to stretch it out. Next, I want to talk about why do we talk about binomials and trinomials. Monomials should be fairly obvious. Of course, they're the building block of all of these, so of course we need to know what those are. But the main feature that we are heading towards as we begin to learn about polynomials is how to factor. And factoring has to do with the relationship between binomials that look like this and trinomials that look like this. So I do want to say that while anything that looks like this can still be called a binomial, the most common binomials you will see as a beginning algebra student will be ones where there is a constant term and an x raised to a single power. Binomials that we call linear because they look like the lines that you will have just learned about. We call this a linear binomial because it looks like y equals mx plus b, right? Which is the equation of a line. And we studied trinomials that most typically look like this. Again, they could be more complicated, but most commonly you'll see an x squared, an x to the first, and a constant term. And here is the y. Let's look at my first example and jump ahead a section or two to talk more about why the term and factor distinction is so important. It turns out that this trinomial has a sophisticated way that you will shortly learn to break it down into this product. This is the action known as factoring. So we factored the trinomial. Into a pair of binomial factors. And here's where our term factor distinction is coming in there. Here, factoring is a verb, so we factored the trinomial, we applied an operation to it, so this is not a noun factor, but the verb factor. Trinomial is referring to it being a three-term object, so we're talking about terms. And then we have broken it down into a pair of factors. So we have taken something that started out with three distinct and relatively simple terms, each made up of separate factors, and we have turned it into two separate factors. And you might be saying, hey, wait, isn't 3x a term and 1 a term, and x a term and 1 a term? Isn't there 4 terms there? And you would be right to some extent, but we need to make sure that we're throwing the right level of categorization into this, and this is why it becomes a complicated topic. If we talk about the whole expression, everything that's on this side of the equal sign, we are actually only allowed to say that there is one term there. We are not allowed to make any claim about there being more than one term there, because everything is held together by multiplication. Within that one term, there are, of course, this pair of two factors. But then we can go one step further and we can say, within the first factor as a chunk, that's where we get our chunking term in there, there are two terms, namely 3x and 1. You can go even one step further and you can say the first of those terms, 3x, is itself made up of two factors. So we see this is quite nested. From the inside out, we have a pair of factors come together as a term. A pair of terms comes together as a binomial. That binomial combined with another binomial comes together as a single compound term that we call the factored form of the polynomial. And if we were to expand that factorization, it can be written in its expanded form as a trinomial, which have a different set of factors and terms. So to summarize where we've come to, when we first learned to read, we saw the idea that separate symbols came together into a unified whole. Or with phone numbers, the same idea. And as long as those wholes are not terribly complicated, we tend to see them as separate pieces. But as those wholes become more and more sophisticated, it takes more of a conscious action to view them as a single object. I very much doubt many people think of CAT as k-a-t anymore. They just see the word cat. They hardly even recognize the letters in it. They can even write it without thinking about it. And it's the same idea with our algebraic skills. It takes not too much to learn the distinction between terms and factors in this expanded form, But when we move to this format and we begin to see terms made up of factors, made up of terms, made up of factors, as it nests deeper into itself, it becomes harder and harder to recognize those chunks. And a sophisticated algebra student will be able to see objects like 3x plus 1 and just think of them as a linear piece. Or think of objects like x plus 1 and think of them as a linear piece, essentially chunking them into a single idea, in this case a single factor married to another single factor to come together as the whole term, and they will no longer be confused to say, well, maybe I see 4 terms there. They will see, I see 2 factors. And if they need to, they can dial it down and look at one of those factors and say, and that factor is made up of terms. And if they need to, and they can say those terms are made up of further factors. But you are able to dial in your level of focus to what is appropriate for the problem at hand and not get confused or mush those things together. And that's where students will get confused. In our next lesson, we will begin to look at what operations can be applied to these polynomial pieces. And to give us just the smallest preview, I want to draw attention to the idea that we can do some basic operations and know most of the tools for them. If I had 3x squared, a factor, and I want to multiply it times 2x cubed, another factor, I can simplify this. I begin by going back to basics and remembering that when I multiply 2 things together, it doesn't matter what order I do the multiplications, as long as I multiply each thing together. For example, 2 times 3 times 4 could be thought of as 6 times 4, and therefore 24, or could just as readily be thought of as 2 times 12, and still equal to 24. Or even 2 times 4 is 8, and 8 times 3 still gets us to 24. So the same idea applies up here, and we will regroup things together to say, well, I have a 2 times a 3, and I know what to do with that. I can call that a 6. And I have an x squared times an x cubed, and I know what to do with that. And if I don't remember how to do with that, I can remind myself, x squared means x times x, and x cubed means x times x times x. So how many x's do I have total? I have 5 copies of x. So that comes together as x to the 5th. And so I'm able to take these 2 separate factors and combine them together into this new simplified factor, 6x to the 5th, what I can think of as a single chunk. Another idea is we're already familiar with the principle of the distributive law. We are certainly allowed to take 3 and distribute it in. We've done this on previous problems and rewrite this as 6x plus 3. But we can also do the same thing if it has variables in it. In the same way, I can distribute this, making this into 3x squared times 2x and a 3x squared times 1. And then those simplify the same way we have done this up here. So this becomes a 6x cubed and a 3x squared. And very importantly and fundamentally, as the main direction we are heading, the distributive rule reads this way, but we could just as readily reverse that and read backwards. When we read backwards, we say that we are in the action of factoring. And when we are reading forward, we're in that action of applying the distributive rule, distributing. So it is possible to take a structure like this and read it backwards to get back to a structure like this. And that's a new skill. This is how we're going to be able to take this binomial and rewrite it in a factored form where it becomes a more sophisticated monomial. There is only one term here because everything is connected by multiplication. There are many factors. 3 is a factor, x squared is a factor, and most importantly, there's this complicated chunk, 2x plus 1, collectively, as a binomial, is a factor. That's what the parentheses do for us, is they identify it as a factor. That is where we're heading. But for now, as you're getting used to this, spend some time looking at different problems, deciding if they are in fact polynomials or not polynomials, counting the monomial terms, getting used to the way they look, and especially paying attention to the differences between what is a factor and what is a term as it gets more and more complicated. It's harder and harder to see, but the practice will pay off, because as you move further and further into your rules for algebra, you will discover that all the distributive laws are about multiplication relative to collections of terms. And if you know that that is a rule that belongs to terms, you won't use it on factors. And you will save yourself many headaches and many troubles. So, good luck to you, and goodbye for now.